Hey everyone, thank you all so much for joining. I am Kareen Wallach. I oversee community at Startree. And today we have a very interesting presentation on geospatial support in Apache Pinot. Our presenter is Yupeng Fu. He's a staff engineer at Uber. He leads Uber's real-time platform and infrastructure, including multiple mission-critical services powered by several open-source technologies like Kafka, Flink, and Pinot. So we're really excited about seeing his presentation. So really quick, just some lay of the land stuff. If you have any questions during the presentation, feel free to ask. There will be some folks here from Startree and Apache Pinot contributors and committers that might be able to answer those questions. If not, we will also be doing a Q&A immediately after Yupeng's presentation. And if you happen to be watching this on demand and not live after the fact, you're also welcome to join the Apache Pinot Slack. And Yupeng is there, and there's also some other amazing people from the Pinot community who can also probably answer some questions too. So yeah, without further ado, welcome Yupeng.
Hello, everyone. Thanks for having me. Today I'm going to talk about geospatial support that I added into Apache Pinot. Coincidentally, we just published an engineering blog on Uber engineering blog series. We'll just paste a link in the Pinot Slack channel. So if you're interested, I can also go there and take a look. So I will cover some of those in this talk as well. To begin with, about myself, I'm a software engineer at Uber. I lead the real-time data infrastructure. So this infrastructure includes many streaming-related systems like Kafka and Flink, and for the real-time OLAP, we use Pinot. I'm also a committer of several open-source projects, including Pinot as well. So let's begin with the why we want to add the geospatial support, and also why we want to add this to Apache Pinot. In fact, Uber's business is highly real-time and geospatial data related in nature. Every day if you open up your Uber apps or UberEats app, there are tons of information sent over the wire, and we actually collect information from drivers, riders, restaurants, eaters, freight carriers, merchants, and those are valuable information. And we use this information for different purposes, like fraud detection, recommendation, and try to derive important insights and provide value to the end users. So just give you one example here that we also highlight as one use case to show why this is real-time useful and why geospatial data is useful in this case. If you open up your UberEats app, if you scroll down, you will see on the home page there will be a carousel called Order Scenario. So this carousel will display people around you order what kind of dishes in the past minutes. So purpose this is to provide some social engagement to the Uber eaters, to let people be aware what's going on around themselves in the real time. This is just one example. There are many other good examples to show the geo information is very powerful. For example, how many drivers or riders in a given geolocation. This can also be helpful for demand-supply balancing and fulfillment. So back to this query to show this order scenario case. So I will talk more in details in this talk, but I want to quickly show you that the entire this feature for the data backend can be simply described as one SQL query like the one below. You can think of that there's one Kafka topic that for people who place orders, this backend survey will send this information to this orders table. And we set up a Pinot table over this Kappa topic. And to retrieve these nearby users in the recent time, it can be as simple as this query with a where clause. You can see there's a function called distance, which is a geolocation function that takes one location st point, which can be like the orders information, and also the current the user location, which can be like a parameterized query function to this. And then we just like check the distance to see if they're like the orders nearby. And also we can put like a time series stamp on this. So this is very useful for the product teams because the backend can be built as simple as running one SQL query. And we leverage Apache Pinot to take care of all the system-related complexities like reliability, availability, and scalability, and therefore improve greatly of the productivity for the product teams to build applications. So in this talk, I will just walk you through on the entire like geospatial features that we added to Pinot, and some of the details on like how we evaluate these functions, how can make this query really fast and scalable. Before I talk about the geospatial feature, just give you a very quick overview of Apache Pinot and Uber. So the real-time platform at Uber, this is a very popular chart on the internet, is trying to perform analytics on the most like recent time and to help the application to make time critical decisions. And we believe for the events time that as time goes by, the value decrease. So this is very straightforward, and there are many good examples to show how we can bring the value from these events when they are like very recent. A few examples to show the major categories of these real-time use cases. So on the left-hand side, you can see this is how Uber does the search pricing. It's a demand supply change. So reflected on the Uber price, Uber rise price. So the purpose is very straightforward: is to encourage more drivers to the location that has higher demands. So to make like balancing of the driver rider markets using price. Another example is for the external analytics. So this reflect as dashboards. On the second diagram, you can see this called Uber Restaurant Manager. So this shows as application to all the restaurant owners, and they can see the most recent performance of their restaurants, including the sales, the popular dishes, the feedbacks from the users, everything just like in real time. The real time also are very important for the machine learning use cases. So if you have used Uber apps before, the third screenshot should be familiar to you, is that how for the Uber Rides and UberEats, we do the delivery estimates. And the so from like time, you can see like if your order will arrive in half an hour or so. Also, they are like these are like predictions made by machine learning models. In addition to that, we also use real time as like monitoring as reinforcement to the machine model to see if this model predicts correctly or like effectively. And lastly, for the Uber internal users and data scientists, we also use real-time data for the exploration and try to derive insights not only on the historical data, but also on the real-time data. For the Uber real-time platform, the core is Apache Pinot. So Uber has adopted Apache Pinot for quite a few years. And based on our observation, Pinot has also very good adoption across industry in the past years, and has a very good validation on its scaling, performance, quiet latency. So far, we are very happy with our choice on this. To add more on this part, so you can see this scale numbers is kind of like reflected on the scale like of Pinot we run at Uber. As you can see, we chose primarily for its high QPI support, low core latency, and very cost effective. We did a lot of analysis and study on the cost storage efficiency side. Because Uber is working really hard towards profitability. So cost efficiency is indeed like a company priority. And we have seen, comparing to many other row-based or dock-based storage, for example, Elasticsearch, Pinot showed a great cost efficiency and cost storage reduction. We actually published a paper in Sigma this year, which is a conference on the database and data management. So this research paper documents about how the Uber real-time data infrastructure is built and the major components, which also includes this kind of like design decisions and how we chose different open source technology as a building blocks. So feel free to take a read if you are interested. So the link is pasted at the bottom of this slide. For use cases, as mentioned that in the earlier slides, that it powers a number of different external and internal platforms and use cases, such as like dashboards. We also invested quite a lot building the ecosystem around Apache Pinot and Uber. So this reflects on how we improve the user onboarding through UI-based workflow management. So that people can just like go there and click a few things and clear some boxes to onboard to their Pinot table. On the query side, we did the integration with Presto, which is also a popular query federation engine originally from Facebook. We published some blogs in the past talk about like how we made this decision and how this Presto help like integrate the Pinot with the rest of the Uber big data infrastructure. So let's move on to talk about like the geospatial feature. So we contributed this feature last year in 2020, and we actually spent quite some time on the design phase to see how we can add this geospatial feature in a future-proof way. So to further explain this, I would say geospatial is actually a special topic in big data management, and it's a pretty complex domain. In fact, there are like CQ standards built around this. There are many commercial databases like try to monetize this area. I think one of the reasons is like this, the geospatial is a complex topic. So in this part of talk, I would mainly mention a few challenges that we observed when we try to design the feature. One of the challenges is that the geospatial has its own data model. So in addition to the plain data model, like in the database, which are people familiar, like you have a string, you have integer, you have double values. But for geospatial, it's actually have abstractions of the geometry hierarchy. So you can see this chart, which is copied from OGC, is Open Geospatial Consortium. It's also like a standard. It has a hierarchy and has a like subtype system. So you can see there um, like concepts like points, curve, like surface, polygons, and there's also like a collection of these data structures. So like give you a few examples, like how you represent some like primitives, right? How you define like point, how you define like a line and string, and a polygon. It has a like rich standard definition of this. So data modeling is definitely like one example. And the other change like coming from this is that how we can perform this data definition and processing like efficiently, how we can encode these values. So like to show you one example, like how if you take like Uber ride and as a route like this example, how they can be represented as like as lines using this geospatial formats. So for the multiples is also a collection of geometry like types. People may be interested like why we need this. Usually this is useful to capture the result of some operation, like for example intersection of difference. To give you one example, like if we take a line and some polygon, if we do like intersection, so the results could be like a collection. Another interesting part is that when people talk about like geometry, there are actually two popular like coordinates. One is a Cartesian based, the other is a spherical. So for Cartesian based is very straightforward. It's like planar coordinates. But the spherical is based on the Earth's shape, right? As used like a different way to encode data, which is like longitude and latitude that we are familiar with. And often these two cannot be used interchangeably. Like just give you a quick example. Like say if we want to find the flight route from Vancouver to Paris, on a planar coordinate system, it's going to be like a line, right? So it's the shortest distance. However, if you take the Earth, if you look at how the plane takes the route, it's actually not. It's not like a straight line on the planar coordinates. So there are additional challenges to take care of this, and there are like different algorithms are used to calculate the distances or areas differently based on what kind of like coordinate like system is used. And because of complexity of this geospatial like hierarchy and type system, there are actually different like formats trying to capture this. We just list a few like popular like standards. And in Apache Pinot, we actually took the vector-based formats, which is the most popular one, and also like widely adopted by many other big data systems. The third part I want to talk about is the geospatial indexing. So this is mainly used for compute efficiently on certain operations or functions on the geodata. For example, you want to do like a join, or we want to calculate the distance. Like one good example is in the beginning slides talk about this Alderson review, like how we can make this data retrieval more efficient. There are like interesting and challenging topics, even in the literature. So you look like these existing and past indexing techniques. There are like different approaches towards this problem, and it's quite well studied in the database like community. So to give you like a sense on this, One popular approach in the past is called like quad tree. It's a way to split is to group the data points using the rectangles, and then to build this tree structure on this. But at Uber, we took a different like approach. So even before we work on these geospatial features on Pinot, there's Uber already made a really good open source library called H3. It's a great library, which takes like a hexagon based approach. So to give you like example to see what this means. So on the rightmost of this, you can see for how we will create the geospatial space using the hexagons. I can see for each hexagon there are like 6 neighbors. This approach has some unique properties comparing to other approaches, the gradients like square based or triangle based. The important property is that all the neighbors has equal distance, which can simplify a lot of the geo-based distance calculation and measurements. And also this hierarchical grid system, which means you can have like a different resolution and this kind of like it's kind of like trade-off between the precision and the computation latency and the complexity. So like give one example is like how you can use this grid system to approximate California, and how you can see how we can split like San Francisco area using the grids. So in the later slides, I will show you how Pinot integrate this with this H3 to build the geospatial indexing and how we use this to speed up the queries. One thing I want to keep in mind is like the hierarchical grid system is different from the circles, but they are just trying to approximate circles. So this presents some unique challenge on how we can compute some exact results. And also in the later slide, I will describe how we overcome this challenge. All right, so let's talk about how we build these geospatial features and then address those challenges we mentioned in the earlier slides. So for the data types, in Pinot, we actually added a full support of the geometry type hierarchy. So just list a few examples here to see how you can create this like geodata structures, how you create like polygons, how you create multiple lines. If you're interested, you can go to the Pinot documents to show to see some more details. One difference that like we did not add this kind of logic types into Pinot type system, but instead we try to reuse the bytes type. And that means all of these functions will create some bytes encodings. And we leverage open source library called GTS, which is also quite popular in the industry. That like for Spark or PostGIS also use this library. And for the data serialization and deserialization, so we provide like functions to convert this data structure like from different like formats. So there are many two formats, which is like called well-known text WKT and a well-known binary. These two ways are represented as like two functions. And it's also according to the CQMM standard. In addition to this, we support both the geometry and the geography. Remember the two coordinates system I talk about. And then these two can be interchanged using the corresponding functions. So the purpose of this is to support different kind of like geo use cases and geo functions. But keep in mind, like some of the functions can only be applied on geometry and geography. And you can get more information about this on the Pinot user docs. And now let's look at how we can ingest the geodata, right? So it's common to see that in your like raw data or in your events, you will have some of the information about the geolocation. Most common case is like you have a longitude and latitude. And all you need to do is to leverage this transform function, which is another feature in Pinot data ingestion, to transform this into a geodata. Particularly, you can see you define the longitude and latitude, and then you create ST points. And now we want to use the geography like format for this. So we can call like to spherical geography. So all of these are built in transform functions. You can just like directly write this into your data config. Okay, now we have the geospatial data available in Pinot. How can we query those? So we support a number of the geospatial functions. So we actually take the ISO standard SQMM. So this standard defines all the functions start with SD underscore, which is like spatial and temporal. So if you're interested, you can go to this website to see the full spec of these SQL functions. One thing I want to call that, so I would say, unlike many other real-time OLAP systems like Pinot, when we try to approach this problem, we want to conform to the standard as much as possible, mainly for the ease of like maintenance and the sustainability of this feature, and also more importantly that inside Uber we also have other big data analytical use cases, and we try to make sure for the user and data scientists who are familiar with the SQL standard can also easily use the functions on the Pinot as well. So instead, we did not try to like rush this feature in with some customized DSL or like syntax, but instead we would rather like take a bit like slower, but try to make sure we conform to the standard. So the geo functions can be grouped into different categories. So there are like constructors, for example, how you can create this from the like WKT or WKB I mentioned in the beginning. And also there are like measurement functions to calculate the distance and area. We can also like store this geodata and serialize this as different types of output. So the link below also points to the corresponding section in the user guide. You can take a closer look at the signatures of these functions and what it does. I won't call that like the geo functions actually there are a lot. So if we take a full look at the spec, and at Pinot we implement a subset of those which are commonly used geo functions. But there are still many more functions to be added. So if you are interested in contributing to Pinot, I think that's also a good area to extend your help. All right, so let's take a look at this order New York case and to see how we like leverage everything we just talked about to run this query. So this leverage the distance function and also the data points creation function. So a nice execution of this query is pretty straightforward. It's that you just take all the order and filter by the time, and then you evaluate this function, and then this can get the nearby orders that you want. But one thing I want to call is that because of the complexity of the geospatial functions, typically a geofunction is much more complex to evaluate than other SQL functions like for example, like arithmetic functions. So if we just execute this query naively, there's going to be like some performance penalty on this. But looking at this use case, this actually have a runs in every single UberEats app. So you can expect there are like a lot of queries to hit on the Pinot servers. And therefore, it's definitely in our interest to make sure this query can run really fast so that we can take more concurrency. So to improve the query performance on this, we actually invest a lot in the geo-indexing support, which is definitely something interesting and unique, I would say, in Pinot. So let's take another look at this query. So assuming we are at the center of the San Francisco, if you take the Uber's H3 grading system, we can grade the San Francisco area like in these grids. And assuming we want some like a distance which can be represented as a circle, right? So we want to retrieve all of these like data points within this circle. So one quick way to do this, like instead of scanning the all the orders across the globe, we just look at all of the like orders in this like blue hexagons, which is the data if we have the H3 index. So it'll be going a little bit deeper into this H3. So H3 is a library. It means that if you give it like a real geolocation, like for example, longitude and latitude, you can construct a H3 index, which is like a hash of long type. So one way to represent this, you can see we can like leverage some of the geo functions from this H3 library to help us to achieve like identify the relevant hexagons. So importantly, there's a like function called k-ring. It means that if you take my current location, assuming this is the center of the world, then we want to find all the hexagons like nearby. So for the k-ring equals to 1, you can see we have like 6 hexagons around it, right? If we take like k-ring equals 2, then we want to find the next circle like around it. So this is the way how we can find any like index within the k distance of this original index. So how we can leverage this? So the algorithm, I would say, is also be like relatively straightforward once we understand how the H3 library works. So assuming we have the center at the San Francisco, then for all the hexagons that are fully contained in this circle, in this like red circle, then we know these are the data points definitely we need, right? So that means we do not need to evaluate data points within these hexagons. in this example, is that all the height count, the distance is 1. Sorry, I think the rest circle little misplaced. They should be like moved a bit higher, but you can get the idea here, right? So, and for the points that like falling into the H3 instance, which is like I can see the second circle that overlapping with this right circle. For those data points, that means we need to do some evaluation. So remember in the earlier slides, I said that the H3 and hexagon-based approach only can approximate a circle. So here, to ensure we can get the exact results, we need to take all the orders from this circle, and we need to run this SD instance function for data points like within this index. This is actually a great reduction of the data that we need to run the functions over, right? So the reduction is like from all the data in any place of this word to only this second like ring of a circle. And we indeed observe great performance improvements using the geospatial indexing. So for the geoindexing creation is also actually pretty straightforward. So on the left-hand side, you can see this is the same data ingestion configuration that we have in the earlier slide. And we can create this index, just say, for this, sorry, I think there's also a typo here. There should be like the group location. We can say the index type is H3, and we can list the resolutions that we need. So some quick comments on the resolution. So H3 has like different number resolutions from 0 to 12 to control the granularity. And for different resolutions like we build here, that can determine how fast you can retrieve these data points in exchange for the storage, which you have to build the index and then you pay extra storage cost to speed up this query. You can refer to this user guide to learn more about how to create the geoindexing. So I want to take a further look into this orders near you because it's a very interesting use case, and it shows many good like gains from the using Apache Pinot as a storage choice. So when the product team first built this new orders near you use case, originally the team used Cassandra as the storage backend. The reason is that for the UberEats orders, when people place an Eats order, the orders are stored in Cassandra. So a natural idea from the team is to reuse the storage and reuse some of the existing backend API. So there's a service called like order gateway for the order process, not only for write, also for read. So for each of these orders, a near you request, this fish runs to retrieve 20 nearby restaurants, and then do some like sorting and find out the relevant orders, which means for each incoming user request, this translates to 20 requests to this order gateway. And for each order gateway, this will invoke 6 key read on Cassandra. And now you can do the math, right? So for each user request, this translates like 120 requests to Cassandra. And this will add a lot of pressure on the Cassandra as a backend. And the team did estimate that they have to increase the existing Cassandra capacity by 6x to support this query load. So the team re-architect the entire backend solution. And this time they use Pinot. It's actually a pretty efficient solution. You can see like for each of the user requests, this only translates to one SQL query hitting Pinot. Not only we saved a lot of backend servers, but also we observed very good query latency improvements. Before, there are so many remote RPC and back and forth calls. It took seconds to fulfill this request. And now with Pinot, we can only take like less than 50 milliseconds, which is great latency reduction. Also, Pinot have this really good inbuilt feature to support horizontal scaling. So if you're interested about this routing technique, there's a link to the Pinot user doc. So this routing mechanism is called like replication group. So you can see on the diagram on the left, by default, Pinot will share the data into different servers, and each server will have like one copy of this data. In total, for each segment of this shard, by default, there are like 3 copies. So by default, the query router will take the query, and it will do the scatter and gather, right? So it will dispatch the subquery to the corresponding like servers, which by default is like uniform to make sure the query load uniform across the servers. But this default approach has a few like issues to support high QPI use case. One is that the default number of serialized replicas might not be sufficient when the QPI is high. Because at most you can only have 3 servers to serve this query of this particular segment. The other is that if any of these server is slow, then you can run into the situation that this will make the entire query slow because of this bottleneck, and this results in the long tail latency issues. So the technique to resolve this is to leverage called like replica group. So each replica group has a full replica copy of the entire table, which means that for any given input query, we can dispatch this query to one replica group and to fully fulfill this query. And all of these replica groups are disjoint. So the way to scale the backend is very easy. It's just like you increase the number of the replica groups as you see more and more QPIs incoming. So this is how we achieve the horizontal scaling. Some additional insights I will gain from this use case is that, which is a separation of the ALTP and OLEP. So for people who are familiar with like database technology or big data ecosystem, this is actually a pretty common paradigm for the batch-oriented data. So there are like popular OLTP engine, like for example, MySQL or Cassandra, that takes business critical like write operations. In this particular case, that is served as the persistent store of the UberEats orders that we do not want to risk this storage system. But for the online analytical queries, they have their own unique like query pattern and loads, and typically this kind of like read query has much higher volume than the write queries. So by setting up this separation using like Kafka as the event log, we can ingest these changes into Pinot, which can be used to take all the analytical queries. Not only this isolation provides higher reliability and fully protect the OLTP storage. But also we can easily scale these servers up and down based on the unequal query loads. And this also makes the query latency much better because the OLAP engine is designed for the unequal queries. It has a columnar store and also has different kind of like index systems, so which is quite different from the traditional transactional store like MySQL or Kiwi store, which are not designed for the unequal purpose. So I want to share like a few useful links. These are geospatial features that we contribute last year. The first set of features was released in the 0.6, and the geoindexing was released in the 0.7. You can find a user guide and also the design doc on the Pinot websites. So Kenny from the community wrote actually a pretty good introduction blog on this to introduce these features. And today, from the Uber engineering side, we also publish a blog to highlight these orders near you and some more insights we gained from this use case, and also to introduce the geospatial features. I also want to take the opportunity to thank Jackie and Kishore from the Pinot community, who helped a lot on both the design and the engineering. So without their help, we couldn't have made these geospatial features available in Pinot so soon. So I will stop here and happy to take questions.
Thanks, Yupeng. That was awesome.
Thank you.
And thank you for all your work on this too, and for everyone else that you shouted out.
Thank you.
So there is a slight delay between the video and the Q&As. So if anybody has any questions, please ask now. You can ask directly in the chat. We do have a couple questions that already came in. Okay, so Mayank asked, curious how the Cassandra cluster size compared against the Pinot cluster size, the number of nodes.
Yeah, so I cannot disclose the exact size of the Cassandra one, but I would say the Cassandra size is definitely much bigger than Pinot cluster. And also, if we time this by 6, it's definitely, I would say, like over like 1 order magnitude of the Pinot cluster size.
Nice. Mayank, I hope that answered the question. Mayank's making a joke. He said, I know what you're thinking, asking a question instead of answering for a change, because he's usually in here answering questions. But he answers the questions so well that we get questions during the event. And then by the time we do Q&A, there's no questions left because he's answered all of them. So Matt asks, how do you protect rider location from staying in the database for an extended period? Are there any GDPR implications in your use case?
Yeah, so that's a good question. So Uber is very serious about the GDPR, and the entire data lake at Uber conforms all the GDPR requirements. But for the like real-time data in this particular case, so for all the data like ingested into this is for the analytical purpose, and we shield all the sensitive information from this. So I would say this is actually another great use of this separation between OLTP and OLAP setup, because for the annual queries, we do not want to directly hit the transactional store, which has more information than necessary for the analytical purpose, right? But when we do the data ingestion using Kafka, the engineers can be like conscious on like what information are needed and only pick necessary information for this particular case. So hope this answers your question.
Yeah, it kind of sounded like, I'm not sure if it's 2 questions or if it's 1 question. Because protecting the rider location from staying in the database for extended period. That you basically addressed that too, right?
Yeah, so also on this, like this, like they are like real-time like information, so that and on the Pinot we can configure the data retention, like how much data I want to keep this. So for this pipeline, like we just need like for a couple of hours to serve this type of like query load.
Got it. Cool. If anybody else has any other questions, please ask now. And if you happen to be watching afterwards, some people join a little late and they start watching the video from an earlier point, so they don't make it to the Q&A right away. But you can always ask in the Slack. You can ping Yupeng directly, or you can just ask in the general channel.
Yeah, feel free to reach out to me. I'm also available on the Pinot like Slack channel, and I would say there are also interesting work on the geospatial part. So if you have interest in this area, we can also follow up on the GitHub issues.
That's awesome. Yeah, that's really cool. That's definitely a big part if you're interested in like being involved in it. Cool. So I don't know if there's any other questions coming in. Sometimes they like flow late because of the delay. But I think we might be good. We are having some thank yous. There was a very awesome presentation. Istvan says very awesome. Uday says thanks to Yupeng. Awesome work. I definitely second that. Mayank said thank you. The feedback is really awesome. So for all the attendees, if you do have any kind of feedback that's specific, it's very helpful to get that. So please share it. Rohit says great session, Yupeng.
Thank you. Appreciate
much. A lot of thumbs up. Make sure all you attendees out there are subscribing, commenting, liking. Definitely give this video a thumbs up if you enjoyed Yupeng's presentation.
Thank you.
Cool. Yupeng, thank you so much for taking the time and breaking all this stuff down. Really, very, very informative.
Thank you.
That's awesome. Can't wait to see what more where this goes. Cool. We got an applause emoji as well. All right, Yupeng, thank you so much for being with us, and yeah, we'll see you in Slack.
Thank you. Have a great day, folks.
Oh, and also, I mean, did you want to mention the blog too, or? Oh
yeah, so I sent the blog to the Slack channel.
Okay.
So I can also. I'm not sure, like, Carrie can see this on my screen.
I can add it to the stream, so yeah.
Oh yeah, so if I can post this.
Yeah, we can post it in the Slack. We also have another question that just came in too.
Oh, sure. Yeah.
Question. See, sometimes the delay is weird. It's like the questions come in super late. Like we were about to close it off.
Sure. Yeah. So
but yeah, regarding the blog
is here. Yeah, about the group by. So yes. So the geospatial are like common Pinot functions, so that you can group by function results. But just keep in mind that the some of the geospatial functions are complex to evaluate. That's why we added the geospatial index support. Like especially when, for example, if you have like polygons, like my favorite example is that you have a city, and the city they have like thousands or even like hundreds of thousands like points to draw the boundary of city, and want to say, oh, whether given their points contain the city, it can take like seconds or to evaluate this, right? So commonly there are like techniques to generate like a city ID or country ID associated with the events for quick filtering or evaluation. So people also do this as part of the pre-processing as well. But for this, working with is more like a general purpose geospatial support, so that you can also leverage as like different kind of like geospatial related like query load. I hope this answers the question.
Cool. Yeah, I think that was pretty thorough. I think that makes sense. But I also included the URL for the blog in the chat. I dropped it in there. So
that's great.
Yeah. Cool, Yupeng. Thanks again. This is really awesome and very informative.
Thank you. Have a good one.
Okay. Bye.
Bye.